Hi everyone, this is a short video to answer the question, what is the law of conservation of energy and what are energy stores? Two lesson objectives: to know and be able to apply the law of conservation of energy, and to know how to calculate some stores of energy using equations. So if we think straight off about the law of conservation of energy, it's that energy cannot be created or destroyed. It can only be transformed into other forms. And you've probably heard that, or derivatives of it. Looking in detail, if we take an example to explain what it means, if we think of a car, and in the car there is a fuel tank, which has got fuel in it to that level there. There is chemical energy stored in the fuel, and the engine converts that chemical energy into kinetic energy, which is the energy involved in moving. That's what kinetic energy is. This idea of stores, so I mentioned the word stores a couple of times. Stores are a useful way of thinking about energy because of the law of conservation of energy. So as there is a store of chemical energy here, it transforms into kinetic energy. So over time, what happens is the chemical energy reduces as it gets used up, and the kinetic energy of the car is maintained. So how much the car is moving is a store. So there is a store of kinetic energy which has come from the chemical energy being transferred into kinetic energy. But as well as kinetic energy, there's also thermal energy given off, and sound will also be given off. So we would say that there is a store of thermal energy which is increased, which goes into the atmosphere. So that store of chemical energy mainly goes into the thermal energy of the car, which is given off into the atmosphere, and also the kinetic energy, which we actually want. So we would class that as the useful energy. The way we show that is by using something called a Sankey diagram, which again is just a useful way of considering these stores. And we can draw the start of an arrow, and this is all of the chemical energy. So we have this value, so this quantity, whatever that value is, say 100% of chemical energy. We can draw some of it going into the kinetic energy store. So I've just used KE as an abbreviation, so the kinetic energy store. And then this amount going into the thermal energy store as heat. And that's quite nice because you can see the proportions of where the energy that you put in where does it go. So this is our useful and this is wasted. It's wasted because we don't want to heat the car up or the atmosphere. What we want to do is get the car moving, but this shows that about 25% of the energy is going into the kinetic energy store, where much more, 75%, is going into the thermal energy store. So a Sankey diagram is useful for that. You can do a more simple diagram which just shows the names of the stores. So we have chemical, and that is the fuel, is chemical energy going to movement, which is our kinetic energy, and that shows the transfer of energy where we want it to go. You might add plus thermal, but this energy flow diagram shows where the energy comes from and where it's going to. Another good example would be looking at the sun. So if we take the sun, and in the sun there are loads of nuclear reactions going on. It's like many nuclear reactions which give off loads of energy, and that energy is transferred to the earth as light, and then plants transform that into chemical energy through photosynthesis. So we've got nuclear energy store, like that, and as that nuclear energy is used up, albeit really slowly because there's so much, it comes down, it's emitted, the energy is transferred as light, and then the chemical energy store is going to go up as the plant turns that light, well, turns the carbon dioxide and water into the molecules that it needs to grow. But again, it's this idea that energy cannot be created or destroyed. It's just being transformed from one form into another. So we've got our chemical energy store being transformed into kinetic energy of the moving car, and the thermal energy heating up the atmosphere, or in this example the nuclear store of energy being transformed into a chemical store of energy in the plant following a process of photosynthesis. So we're just going to look at some specific examples of energy stores that you need to know the equations, you need to be able to remember these and use them. So kinetic energy is to do with the energy associated with moving, and those are objects with mass. So if you have a mass, an object that is moving, then it has a kinetic energy store. So how do we calculate the quantity of kinetic energy? This was an experiment, and two scientists were looking at objects that were moving and the energy involved. So this was Gottfried Leibniz and Johann Bernoulli, who did work on this and came up with the equation. So they worked out that the kinetic energy store, the quantity, the amount of kinetic energy that a moving mass has is half times the mass multiplied by the speed or velocity squared. So what does that mean? If we have any object with mass measured in kilograms, and if it is moving at certain velocity. Now you hear that word in physics, velocity. What it means is an object has a speed and a direction, so it's one word that links the speed and the direction. So here I've given the direction going towards the right, and let's say it has some velocity v, meters per second. So if I know what the mass is, let's say it is 5 kilograms, and I know what the velocity v is, let's say 3 meters per second, I can simply put that into the equation to calculate what the energy store is. So the kinetic energy store here would be 0.5 multiplied by 5 multiplied by 3 squared. So either working off the calculator or doing it the arithmetic in your head, we're going to square the 3 to 9, multiply by 5 is 45, and then half it is 22.5 joules. And J stands for joules, which is the unit of energy. You might also hear the word kilojoules in a bigger system, where kilo is 1,000, so that's just 1,000 joules, or even megajoules, where mega is 1,000,000. But in this example, really small example, 5 kilogram mass moving at 3 meters per second will have kinetic energy of 22.5 joules. So kinetic energy is the amount of energy associated with a mass moving at some speed. If we look at another form, I want to look at gravitational potential energy. So if we consider the Earth, and all around the Earth there is a gravity field attracting objects towards it. So that could be attracting you to the surface of the Earth, or attracting a stone that you've thrown and it's going to come back, and it's gravity that attracts that object back to Earth. So gravitational potential energy is about thinking about taking an object, again with mass, and moving it against gravity to a place that is higher up in the gravitational field. So let's call that H. Okay, so that, and you can imagine that. You can consider it in your head, do a thought experiment. If you take an object and you lift it up, then you need to use some of your energy and use that energy to lift the object up. And there is an equation that you can use to work out how much gravitational potential energy you've given something when you lift it up, or when it gets lifted up in the gravity field. Okay, so what we've got here, a new symbol. This is delta, and in physics, delta, it's a Greek letter, so shown as a little triangle, means change in. So that's what it is. So delta means the change in. So if we know the mass of the object, we know the strength of the gravitational field, and we know the height change, then we can work out how much energy has been put into that system. So let's say that our mass is 5 kilograms again. We need to think about this value for gravity. Now, the gravitational field strength depends on the size of the object, which is the Earth, and other things. At GCSE, we know, and we can use the fact that gravity of Earth is 9.8 newtons per kilogram. So it's a known value that you can use and remember. And let's say that we change the height by, I don't know, let's say 7 meters. I'm going to push that through my calculator. So I've got my mass of 5 multiplied by gravitational field strength 9.8 newtons per kilogram, and then a height of 7 meters gives 343 joules. Any object with mass that is lifted in a gravitational field, lifted by a height of whatever, that is how much energy the object now has available. I use the word available because it is potential. So if you were then to drop the mass back, then the gravitational potential would be released, and actually it would then turn into kinetic energy. So the kinetic energy store would increase as it fell. Okay. And the last saw I want to look at is elastic potential energy. A good example, got a catapult, and it's been stretched back, so been stretched from its slack state, and it's ready to throw this stone. At the point before you release, there is energy stored in the elastic. or spring. So this, I'm using the elastic to try and get the link for you, but this works in anything that springs back to its original shape once it's released. So I've stretched it. Let's say it was an extension, so it would normally be that length, and then I'm moving it to this length. That is being pulled back some extension in meters. And whoever's using this catapult must be applying a force there to pull it back. That's in newtons. And the elastic potential energy that is stored in the spring is half times by the force times by the extension. So doing an example, let's say that there's a force of 8 newtons and an extension of 30 centimeters. We can just put that through our calculator, so we do 0.5 multiplied by 8 multiplied by, now then, centimeters, so I'm going to convert that to 0.3 meters to the base unit. 0.3, whack it through the calculator. It's 1.2 joules. So now we're going to move on to this idea of work done. It's not an energy store per se, but it's a really helpful phrase, which is a way of thinking about how much energy is needed to force something over a given distance, and that's what work done is. So there's an equation that links force and distance, and again, as humans, we have to push things and pull things and move things, and that all involves force, and what this equation does is it considers how much energy has been used in order to make that movement. I'm going to do two examples. So the first one's really simple. So let's say that I've got an object which is on the floor, and in order to get the object to move, I've got to apply some force F, and by doing that the object moves, and now it's here and it's moved from there to there, some distance. So now we're going to move on to this idea of work done. So now we're going to move on to this idea of work done. It's not an energy store per se, but it's a really helpful phrase, which is a way of thinking about how much energy is needed to force something over a given distance, and that's what work done is. So there's an equation that links force and distance, and again, as humans, we have to push things and pull things and move things, and that all involves force, and And what this equation does is it considers how much energy has been used in order to make that movement. I'm going to do two examples. So the first one's really simple. So let's say that I've got an object which is on the floor, and in order to get the object to move, I've got to apply some force F, and by doing that the object moves, and now it's here and it's moved from there to there, some distance. And imagine doing this yourself. You can feel in your how it would force against the object, how you'd push it, and then you'd end up using energy to do that over the given distance. And the work done, so this is just a term which is, it's the idea of energy basically. So it's how much energy has transferred during this time, during this operation of moving the object from here to here. So how much energy, so it's in joules, is the force that's been applied, measured in newtons, multiplied by the distance, measured in meters. That's a really simple example, but let's say that this force is 10 newtons and you move the distance 1.5 meters. How much energy? Then it would be 10 newtons multiplied by 1.5 meters. How much energy has been transferred during that? It would be 15 joules. Super simple. Take another example, little bit more involved, and it's again this idea of energy stores. So here we've got our trusty little car, and it's moving along with some kinetic energy. Just make up a value. Let's say it is 15 kilojoules, so 15,000 joules of kinetic energy. And suddenly the driver sees something and applies the brakes. So the brakes go on, and the car stops in 7 meters. Now what's happened there is the kinetic energy store at this point here needs to have been reduced to 0 by the time you get to this point. So by the time we get from here, from here to here, the kinetic energy store has reduced down to 0. So where's the energy gone? So what has happened is the brakes have been applied here, so there's a force being applied, and as the brakes heat up, the kinetic energy store turns to thermal energy, so the thermal energy store goes up. remember this idea of conservation of energy. You can't destroy it, but it can change. So we've got the kinetic energy store is being transferred into the thermal energy store, and because we've had 15 kilojoules, then at the end the thermal store must have gone up by the same amount, so 15 kilojoules. So the thermal energy store has gone up by 15 kilojoules. So we started by saying that we had 15 kilojoules, and then over a distance of 7 meters there was a force applied. The force on the brakes caused the thermal energy to rise, so we had a transfer of kinetic energy to thermal energy. And we can use the work done equation to work out what that force must have been. So we've got work done. Now the work done by the brakes, the amount of energy transferred is that 15 kilojoules of kinetic energy. It's the work has been done on this kinetic energy to turn it into thermal energy. So we've got 15 kilojoules of work done, and we know the equation is force times distance. We don't know what the force is, so I'm going to leave that as an unknown, F, and then put 7 meters there. I'm going to rearrange the equation, so I do that by doing the opposite operation, or on this side of the equation. So it's 15 kilojoules divided by 7 meters. Let's do it fully then. So force times 7 over 7. So I've done the same thing to both sides, and over here that's going to cancel, so they are going to cancel to 1. So I'm left with 15 kilojoules over 7 meters gives me the value, which is the value for the force, which in this example that is 2.1 kilonewtons of force. So I started with my kilojoules, so that kilo prefix follows all the way through. So the 15 kilojoules divided by the 7 meters leaves me with 2.1 kilonewtons of force has been applied over that distance, and that is how we convert the kinetic energy to thermal energy, by doing this idea of work done, being the energy transferred at the brake, and using the equation to work out what the value of force that was applied to do that. Okay, the last little bit of this video is to consider this idea of useful and wasted energy, and the way that that is compared is by considering efficiency. So efficiency is the comparison, if you like, of where you want the energy to go compared to how much energy has come in at the start. And as I started in the video looking at Sankey diagrams, I think it's a really nice way of thinking about this. So if we've got an input energy, so of 1000 joules, and this is, say, for example, it could be anything at all, but let's go chemical because we can kind of easy one to think about if you think about food that you eat is chemical energy, and then you transform that into thermal energy to keep you warm and kinetic energy to help you move, things like that. Or if you think about the fuel going into a car from that first example, it's an easy one to visualize. So we've got 1,000 joules of energy going in, and if I say there's 250 joules of kinetic energy going into the energy store, the kinetic energy store of the car. So this is a little toy car, say, where there's 1,000 joules of chemical energy going in and 250 joules of kinetic energy. Now we want the car to move, so when you're thinking about your efficiency, you need to think what is the useful energy. So efficiency links useful energy and total input energy. So this is what I want. Happy days. What I don't want is any heat being wasted. So heat energy or thermal energy is very often the energy that we see as being wasted. And the Sankey diagram, same as before, shows that if I have 1,000 joules of energy coming in, I can't create any more. It has to be that block. I can transform it into different types of energy, but I can't lose any or create any. So if I've got 250 joules of kinetic energy, which is useful, and I've got 750 joules of wasted energy. The efficiency, so the equation that links this, is really easy. It's useful energy divided by total input energy. And then if you want that as a percentage, then you multiply by 100. So in our example here, I've got 250 joules divided by 1,000, and then if I was to multiply by 100, again you can use a calculator, or this one is pretty easy to work out, is 25% efficient. So of all of the energy that I put into this system, quarter of it goes to where I want it to, but the majority, 75% of it, is wasted. And whatever the system, whatever examples you're looking at, you can always work out the efficiency of it as a percentage, thinking about the useful energy and the total input energy. So just going back to our lesson title, question and objectives. What is the law of conservation of energy, and what are energy stores? And being able to know and apply the law of conservation of energy. That is the law. The energy can't be created or destroyed, only transformed from one to another. The energy stores that we've looked at chemical energy, thinking about fuels in cars. We also very briefly thought about food. I mentioned the food that you take in, that's like your fuel, and you use that to keep your thermal energy store where it needs to be, and your movement and other forms of energy that you use. We've considered kinetic energy and the equation, which is a half mass times velocity squared. We've considered the gravitational potential energy, which is mass times gravity times change in height. So that is if you've got an object that you lift in a gravitational field, then that's how much energy you will put in. And we've also looked at elastic potential energy, so how much energy is stored in a spring or piece of elastic which can spring back to its original shape, is a half times the force stretching it multiplied by the extension, so how much it's been extended. We thought about work done, which is not an energy store specifically, but it's really useful when thinking about forces and the distance that you apply the force over. And finally, we were looking at efficiency, which is useful energy over total. So you think about where the useful energy is that you want, divided by the total energy that goes in, and if you multiply by 100, the value is in percentage.